Imagine waking up one day to find gravity has become a little weaker, not enough to notice in your coffee cup, but enough that the moon's orbit shifts outward by a few centimeters. A week later, the planets start drifting. A year later, the Milky Way begins to loosen at the edges. And then, on a schedule that feels almost cruelly precise, everything unravels. Galaxies, stars, planets, atoms, even the fabric that tells here from there. This is the Big Rip, the most dramatic ending the universe can offer. Not a collapse, not a fade to black, but a cosmic tear that accelerates until space itself becomes the executioner. The twist is that this isn't driven by some exotic explosion. It's driven by something we already think is real, something we measure in the sky every night: dark energy. And the unsettling question is simple. If dark energy can push the universe apart, what happens if it learns to push harder? For most of human history, the universe was assumed to be static and eternal. Then, in the 1920s, Edwin Hubble showed that distant galaxies are rushing away from us, and the simplest explanation was that space itself is expanding. That discovery turned cosmology into a detective story. Expansion suggests a beginning, and gravity suggests a slowdown. For decades, the default expectation was that the universe should be decelerating, like a ball thrown upward, because everything with mass pulls on everything else. Astronomers argued about the details. Would the universe expand forever, coasting more and more slowly? Or would gravity eventually win, reversing the expansion into a big crunch? There was an extra complication Einstein had introduced and then regretted: the cosmological constant, a kind of built-in energy of space that could counteract gravity. He originally used it to force a static universe, then abandoned it after expansion was discovered, calling it his biggest blunder. Still, the idea lingered. Maybe empty space isn't truly empty. In quantum physics, even a vacuum seethes with fields and fluctuations. If space has an inherent energy density, it might behave like a pressure that affects cosmic expansion. Then, in the late 1990s, two teams studying distant Type Ia supernovae made a startling measurement. These exploding stars act as standard candles, letting astronomers compare how bright they should be with how bright they appear, and thereby infer distance. The results implied the expansion of the universe isn't slowing down, it's speeding up. Something is acting like anti-gravity on the largest scales, dominating the cosmos today. We named it dark energy, not because it's literally dark, but because it's obscure. It doesn't clump into stars or galaxies, and we mainly infer it from how it shapes the geometry and history of the universe. The comfortable, conservative version of dark energy is the cosmological constant, a steady, unchanging energy of space. But cosmology doesn't just ask what fits the data now, it asks what happens next. To understand the Big Rip, you need one key idea. In general relativity, it's not only mass that gravitates, pressure does too. In everyday life, pressure is just forces in a fluid. In cosmology, pressure is part of what tells space-time how to curve. Dark energy is special because it has strongly negative pressure. A useful mental model is to imagine space as a stretchy fabric with a built-in tendency to expand. Matter and radiation dilute as space grows. Spread the same particles over a bigger volume and their density drops. But if dark energy is a cosmological constant, its density stays the same even as space expands. That means as the universe gets bigger, the total amount of dark energy stuff effectively increases because there's more space to contain it. Normal expansion is like a tide that slowly rises. Phantom energy is a tide that rises faster the higher it gets because the water level itself causes more water to appear. At first, you don't notice. Galaxies still form, stars still shine. But eventually, the repulsive effect of dark energy overwhelms all binding forces, one scale at a time. First, galaxy clusters can no longer hold together. Galaxies drift apart faster than gravity can reel them back. Then, within a galaxy, stars lose their grip and fly away. Later still, planetary systems unbind as the outward stretching between the Sun and Earth outpaces the Sun's gravity. And in the final moments, the effect becomes so intense that it could overwhelm electromagnetic forces, shredding molecules, then atoms, then nuclei. This isn't just poetic doom. You can, in principle, calculate a timetable once you choose. In a famous 2003 paper, Robert Caldwell and colleagues outlined how a big rip would unfold if we were significantly below -1. The end comes at a finite time in the future, not an asymptote trillions of years away, because the expansion rate diverges. The scale factor, which measures the size of the universe, blows up to infinity in a limited number of years. The exact numbers depend on W, and today's measurements suggest W is close to -1. Consistent with a cosmological constant. That means the Big Rip is not the leading suspect. But the possibility stays on the board because measuring W precisely is hard, and because some models allow W to vary over time. The Big Rip isn't the default ending. It's the nightmare ending hidden in the error bars. Even if the Big Rip never happens, thinking about it matters, because it stress tests our understanding of the deepest laws we have. If W is exactly -1, dark energy might be vacuum energy. And then we face the cosmological constant problem. Quantum theory predicts a vacuum energy density enormously larger than what we observe, off by a factor so huge it's hard to even name. If W differs from -1, dark energy might be a dynamic field that changes over cosmic time, like a new kind of substance permeating space. If W is less than -1, that's even more provocative, because many phantom energy models flirt with instabilities. They can imply negative kinetic energy, or allow catastrophic particle production, or break assumptions about causality. So, a Big Rip is not just a dramatic fate, it's a signpost that our current equations might be incomplete. There's also a philosophical jolt here. We're used to thinking of the universe as a place where forces act within space. The Big Rip flips that intuition. Space becomes active. The arena turns into a player. And it reminds us that the biggest effects in cosmology aren't necessarily driven by the biggest objects, but by the properties of emptiness itself. That affects how we plan the next generation of surveys, mapping galaxies, measuring supernovae, using gravitational lensing, and reading the faint patterns in the cosmic microwave background to pin down W and its evolution. We're not just measuring distances, we're interrogating the fate of everything. So where does that leave us? Dark energy is real in the sense that something is accelerating the expansion, but its identity is still unknown. If it's a cosmological constant, the universe expands forever into a cold, sparse heat death, with galaxies disappearing beyond our horizon and stars burning out one by one. If it evolves, the ending could change. A gentler drift, a sudden transition, or in the most extreme scenario, a Big Rip that ends the cosmos on a deadline. The Big Rip is less a prediction than a warning. The universe's future depends on a single number we are still chasing to the second decimal place. And that might be the most unsettling part. The end of everything could hinge on the physics of nothing. If you want more deep dives into the ideas that decide the universe's fate, subscribe.